All right, well, I'll get started here. So yeah, next week's the finals. So whatever happens today is pretty much it. So I'm going to do my level best to get to the so-called Gauss-Bonnet theorem and try to circle back to the things I said day one about triangles and the angle excess theorems. Because next week we'll have the final. So yeah, next week we'll have because I just found out, the last day of classes is the final. And then, so the final exam, in-class final exam will be next week, and then I'll have take-home test 2 due the Tuesday after that. I should make an announcement about all of this, of course, and try to tell you more about, what's on that in-class final. Certainly, it will cover the things we covered in test 1. Now, I should have your test 1 graded like by Monday, so you can get it like next Monday or whatever. Sound like a plan? Okay. So we have reached section 7.3, and so this is my old lecture 25. So like today, I'm hoping to cover old lecture 25, 26, 27, and I think 28. Which are based on chapter 7 of O'Neill. And I'm going to do my level best to try to condense some of these ideas, just get to the point, all right? So section 7.3 is on the covariant derivative. And so what's the covariant derivative on a surface? All right. And so covariant derivatives, I say, they're part of the intrinsic calculus of a geometric surface. We need them to study curves and so forth. So just to sort of get to the point here, we can let's see here. Let's let E1 and E2 be frame on M, at least locally, okay? And suppose you've got a vector field W, which is equal to, say, F1E1 plus F2E2. So what I'm saying is that F1 and F2 are the component functions of the vector field W with respect to the E1, E2 frame, all right? Then for vector field V, so this is my symbol for vector field on the surface, all right? For V, a vector field on the surface, we can define the covariant derivative of V, rather of W with respect to V, is equal to, here it goes, V of F1 plus F2 omega 2(1) of V, all times E1, plus parentheses V of F2 plus F1 omega 1(2) of V E2. Now here, omega 1(2), the connection form given by E1 and E2. So how did we talked about this last time? If we have a frame, how do we get the connection form? Do you guys remember? What was our, we had a whole circle of ideas how to get the connection form from E1 and E2, right? Remember, how did it go? we had the dual, I'm right up here. So we had like the dual frame theta 1, theta 2, right? And remember, and we had that d theta 1 was omega, how does it go? Omega 2 theta 2? And d theta 2 was omega 2 1 wedge theta 1, I think. And those implicitly defined the connection form omega 1 2 from the coframe, right? So exterior derivatives of the coframe implicitly define the connection 1 form through that red equation I wrote up there. And what else did we have? We also had the definition of the Gaussian curvature. What was it? It was, how'd it go? d omega 1 2 equal to, what was it, minus k theta 1 wedge theta 2, I think? Yeah. So these equations here, right, these equations, not that we need the Gaussian curvature at the moment, but these equations are what define this omega 1 2, right? And of course, omega 2 1 equals to minus omega 1 2. But once you have a frame, you can find the dual frame. From the exterior derivatives of the dual frame, we define the connection forms, right? Okay. And then, so a covariant derivative, all right? What is a covariant derivative? Well, the idea of a covariant derivative is to take the object that you're given, right? And the covariant derivative of an object will be an object of the same type, all right, which is in some sense a derivative of the given object. So for the covariant derivative of a tangent vector field to make sense, it should again be a tangent vector field. And that's the case here. This is manifestly a tangent vector field because notice that it's a linear combination of E1 and E2, which are tangent vectors to the surface, right? And V of F1 and V of F2, that's kind of what you would expect for just a plain derivative. And this other term here is kind of new and interesting. The omega 2 1 and the omega 1 2 terms, these are describing how the change in the basically the derivative of W, it has two different parts. The one part is the change in W is coming from how the components of the vector field W change in the V direction, right? That's these VF1 and VF2 terms, right? But the other place that the covariant derivative accounts for the change of W is with respect to like the rotation, if you will, of the E1, E2 frame, which are captured by the connection coefficient. The connection coefficient 1, 2 is in some sense describing how E1 and E2 evolve from point to point, one to the other. And again, the components of W play a role in that. They give weights to this here and there. Okay, so quick note. What would happen if we look at the most simple surface to think about is just the plane? What does this formula look like for the Euclidean plane? For m equal to R2, right, we have E1 equals to just, constant vector field, right? And E2 is this constant vector field, right? So essentially, E1 is partial x, E2 is partial y, and the coframe is dx. The coframe here is dy. So d theta 1, d theta 2, 0, 0, right? So the connection form for the plane is just 0, and the Gaussian curvature is also 0. And how does the covariant derivative look like in the plane? So the covariant derivative of a vector field in R2, according to this definition I have above, would just be V, I'll go back to my usual notation, W1, E1 plus V of W2, E2. But of course, we could notice that that's really just U1, right? And that's just really U2 going back to the notation at the start of the course. So in other words, this covariant derivative, the surface covariant derivative, is just the plain old covariant derivative we talked about at the start of the course if we specialize to a plane. But generally speaking, the covariant derivative on a surface, it is somehow, it is capturing, the nuance of the surface, the curved aspect of it is all rolled into these connection coefficients. Now, in O'Neill, he doesn't quite say it the way I'm saying it. He has some lemmas, he builds up to this point, but if you really distill what he says down, he's basically saying you can define the covariant derivative on a surface by this formula. He shows, now when you do something like that, it begs a question, right? Which is, okay, so if that's the definition, is there just one, first of all, you can't always find a frame that goes over the whole surface, right? That's one problem. So if that's not the case, then the picture is something like this, right? Here's your surface. There's some kind of something in the middle. I don't know, something keeps you from making the frame over the whole thing, right? But maybe you have, you can define the frame on half of it, You have like E1, E2, say, over here, right? And then you have, let's say, E bar 1 and E bar 2 over there. And there's some place probably on the surface, if these two frames cover the whole, the whole thing, there's probably some place in the middle where they're both defined, right? So on this intersection region, you have both, right? So in the intersection region, you can compare, let's say, this formula, which we maybe would refer to as del. And with using the barred frame, we'd have del bar, right? And you could compare the formula in the frame versus the barred frame, right? And if this is going to be a good definition, then we ought to have, well, what should we have? We should have that the covariant derivative of V with respect to W using the unbarred technology is the same as the covariant derivative of V with respect to W using the barred frame at the points where they agree. All right? And this is shown. This is shown in O'Neill. And it's just a simple, well, it's not simple, but it's a somewhat lengthy calculation that's straightforward enough. And it essentially rests on working through a couple different things. Like the key to, I'll just tell you, the key aspects to showing this are, one is that, E bar 1 is cosine phi E1 plus sine phi E2, right? And E bar 2 is, what was it? I guess it was minus sine phi E1 plus cosine phi E2, is that right? I think so. So that's how we know that there has to exist an angle that relates the frame without the bar to the frame with the bar. like you got to be able to rotate one to the other because they're both orthonormal frames. There has to exist this angle function to rotate one to the other on the overlap. And we also, remember last time we showed that if you calculate the connection form on the overlap of two frames, it works like this. Omega bar 1, 2 is equal to omega 1, 2 plus d phi. So on page 21 of my lecture 25 notes, all right, I show explicitly that if you make these identifications, you can prove that the covariant derivative of v with respect to w is the same whether you calculate it from the barred or the unbarred frame. Because they have to relate like this, and when you sort through the mechanics of this formula, they work out the same. Now, there's more. There's more than just this. O'Neill, says that there exists a unique, in fact, there exists a unique covariant derivative which satisfies certain properties. The properties being, what are the essential properties that the covariant derivative has to satisfy? I'll write them down. So the properties are, the covariant derivative of AV plus BW acting on Y is A times the covariant derivative of V acting on Y plus B times the covariant derivative of W acting on Y. So it's linear in that sense. And it's also linear in the following sense. AY plus BZ that's still a V. So here A and B are constants, although I think you could elevate these to functions on the first one. But the third one, we have a function times y, covariant derivative of v of a function times y, function times a vector field. Then we get this Leibniz rule, which looks like the following. V acting on f times y plus f times the covariant derivative of v of y in the v direction. There we go. And then 4, which I regret writing down here, v acting on the inner product of y and z. And remember, this is this newfangled inner product where this could be a really interesting, funky metric on the surface, right? It doesn't have to be the dot product here. I'm talking about that abstract metric idea from last time, all right? Covariant derivative vy z plus the inner product of, I should say the metric of y with the covariant derivative of v in the z direction. So these 4 properties here, all right, so what O'Neill tells us is that there exists a unique covariant derivative on the surface, all right, which satisfies these 4 properties, all right? And when you study his proof of uniqueness, what you find out is what he says is to define that unique covariant derivative, you use this formula. So this formula defines the unique covariant derivative which satisfies these lovely properties. Go for it.
On the second property where you say B plus B.
BZ?
No, like on the other side. Yeah. What is that, B or W? That letter. Or is that not a letter right there at all?
This is supposed to be V. I wrote a W, but then I thought about my life. Said, nope, it's supposed to be a V. The one above is a W because it came from over there. But all right, so again, the covariant derivative on the plane just drops back to be the plain old covariant derivative. All right. But the larger point is here, given a geometric surface, right, which doesn't have to be, a geometric surface is the term we use for abstract surface also. Like a geometric surface doesn't have to be inside R3, it could be inside R4, R6, whatever. The point is it's a two-dimensional space that has a metric on it, right? If you have a two-dimensional space with a metric on it, you can define the coframe, you can calculate the connection form, and then you can use the connection form to build this here covariant derivative. And it has these properties. And it's unique, given the metric. Okay? And again, the proof of that is given on pages 18 through 21 of my handwritten notes, and also in O'Neill, my lecture 25. Now, that brings us to a definition. If we have a curve, so I is a subset of the reals, right? And M is our abstract surface. If this is a curve, and Y is a vector field along W, or vector field along the curve. All right. And that means this language right here, this means that the mapping T to Y of alpha of T, which is, of course, another notation for Y of alpha of T, is an element of the tangent space at alpha of T of M for all T in the interval. All right, that's what we mean vector field along alpha. Then the covariant derivative of Y along alpha is denoted Y prime and is defined by the following. Y prime is equal to, all right, so here, I mean, I should mention, for Y equals to F1E1 plus F2E2. So I'm using F1 and F2 for the E1, E2. Throughout this talk, right, throughout this lecture, E1 and E2 is an orthonormal frame to the surface. Orthonormal in the sense of the metric, which is given on the abstract geometric surface. So F1 and F2 are its components, all right? And then the covariant derivative is then defined as follows. F1 prime plus F2 omega 2, 1 of alpha prime E1 plus F2 prime plus F1 omega 1, 2 alpha prime E2. Where F1 prime is dF1 dt, and F2 prime is dF2 dt, and what's alpha prime equal to? Yeah, I mean, you could say it's d alpha dt. Sorry, I'm trying to think of the proper way to define alpha prime here. I mean, it is the velocity to the curve. We defined the velocity to a geometric curve on a surface before, I think. So, yeah, but the question is, what does alpha prime mean here?
Is alpha prime not the function that maps I? Or
Well, the thing is m.
yeah, is it from I to n? Is that what you're saying?
So, for alpha prime to make sense, right, it has to be a tangent vector to the surface. Just a second here. Let me see if I can find it right away. I was preparing for class today, and it didn't. The abstractness of this had not dawned upon me until just this moment. I'm pretty sure he's defined it in chapter 7 earlier. I am hoping. But I could be wrong. Let's see here. All right, maybe. All right, come on. Where did you define? Maybe chapter 5, maybe. Maybe chapter 4. Probably. Yeah, I think it may be section, maybe section 4.3 actually. Yeah. So here he fesses up the alpha prime is xu a1 a2 dA1 dt plus xv a1 a2 dA2 dt. Now you got to wonder, like, what is this A1, A2 business, right? So this goes back to an earlier discussion. So here's our surface, right? And it's easy to like miss this, right? But if this is alpha, then here's D, and your patch takes D up to M, right? And suppose that the curve lies in the image of this, x of d is a subset of M. It doesn't have to, the patch doesn't have to cover all of M, but the point is the curve. We're thinking about the curve right here. We're thinking about this point. What's alpha prime at that point, right? So what's done, this is a little bit sneaky, but you think about the inverse image of this curve under the x map. So like back here, there's a curve. And that curve is x inverse composed with alpha. So that is itself a mapping from I. So alpha goes from I to M. Well, let's say it goes from I to, well, I'll say M. But then x inverse takes you back to D, which is a subset of R2. So this thing, x inverse composed with alpha, is a function from the reals to R2. So it's a pair of functions, which we call A1 and A2. And so there, you can just straight calculate the derivative. Like the corresponding point back here, you can calculate the dA1 dt, dA2 dt. It gives you just a straight derivative curve in 2 dimensions, in the VU plane. And then essentially you just take that and you push it forward, over to here really, to get the velocity. That's actually the idea here. And this is what that is. But keep in mind that this could also be written, like you could also write this sort of more cutely, if that's a word. You could write this more sort of sneakily. You could write it this way. It's really dA1 dt partial u plus dA2 dt partial v. And I kind of like that way of thinking about it, where the partial u and the partial v are where they're at alpha of t, right? So anyway, just, confession, the velocity for a curve in an abstract surface is itself, it's a little bit involved to really calculate it from base principles. But don't be too scared by this either. What happens again if we go back to our plane example? So for the plane example, this x is just the identity map. Yeah. So the curve is that curve. They're the same curve, and this just drops back down to our Calc 3 to find the velocity, you differentiate the components, and put them in a vector formula. But for more abstract things, like if you had, for example, a sphere, right? And you had a point on the sphere, you had a curve going through that point, and you want to find the velocity to that, curve here. Well, the velocity to that curve should be something in the tangent space, right? So if you actually had the formula for the curve through that point, it would be a linear combination of like the derivatives of the component functions, and then these would be actually in the direction of the partial velocities to the patch on the sphere.
Does the velocities, do they have to be on the surface too? Or can they come off the surface?
The velocities,
Like they will start at the surface, obviously.
well,
They come up off of
they always come, if the surface is, curved, then yeah, the velocity vectors are going to, like if you could look at it from outside, they're going to not be in the surface, they're tangent to the surface, right? But the velocity should be in the tangent space, because on the flip side of things, if I had the parameterization of this in 3 dimensions, alpha of t is like alpha 1 of t, alpha 2 of t, alpha 3 of t, and I just calculate the derivative of that and get d alpha 1 dt, d alpha 2 dt, d alpha 3 dt, that 3-dimensional tangent vector is going to fit in the tangent plane. That's still true. It's just like I'm going through the mechanics of what's involved with writing a derivative, which is really just in terms of the surface calculus, which involves only partial u and partial v. Is what's making my conversation complicated right now, is because I'm trying to do it just in terms of the tangent space to the surface, which I can't go back to 3 dimensions and go, well, there's alpha 1, alpha 2, alpha 3, just differentiate component-wise, and then you can see that that 3-dimensional vector is fitting in that 2-dimensional tangent plane. I mean, it is, but again, I'm trying to. Sorry, I didn't want to get dragged into all this. This is kind of like a little bit of a digression. So we have a velocity, and excuse me, we have a curve, alpha, and we've got a vector field along the curve, and now we're defining the covariant derivative of the vector field along the curve, right? So the covariant derivative of a vector field should again be a vector field. And you notice there's like a very strong, what's the word? Similarity between the formula about the box in purple here, or I guess it's magenta, and my other magenta formula, right? Like, look at these. Very much the same spirit for the formula, right?
Yeah, but
Mhm.
if you rewrote the definition, oh, that's on W though. When you get, if you rewrote the def, when you get the F1 prime of V, right? That's the definition. I'm looking at the definition. You get F1 prime of V plus.
Oh, well, I can't, this definition doesn't apply to this context. Here I have 2 vector fields. Contrast, over here I have a vector field and a curve.
Okay.
They're not the same
So
animal.
you're saying that there's a similarity between curves and vector fields?
I'm saying there's a similarity between these definitions.
Oh, okay.
They're both accounting for the change in the object being paired to 2 things, the change in the object and also the way the frame is rotating at point to point along the surface. I do think there is a connection between the two. I think we get to that soon, but
What can we conclude?
well, this is a
Direction and the change of
well, I don't think we can conclude much of anything at the moment. We have a couple of definitions. We'll have all kinds of conclusions very soon. So just hang on here for a minute. Now, so the this leads us to the definition of, so we have velocity. The velocity is kind of buried behind a push-forward idea, essentially. It's here. Acceleration, though. Acceleration on a surface is now something we can define. All right, because what's acceleration? Alpha prime prime.
oh yeah.
So here it is. Acceleration of alpha on M is alpha prime prime. But you got to be, I tell you, you got to watch out for this here.
Do they have class?
No.
What?
Oh, okay.
No.
Are we missing somebody?
No.
Okay.
Well, that was the question.
Hughes. Yeah. Okay. This guy.
Okay. Okay.
So would you just take the derivative of alpha prime?
So yes, but this is what this means. So this is a very slippery formula because the prime is being used in 2 different ways here. The first prime is the prime described by the velocity construction.
Second prime. Wait.
The second prime,
Why is it? Why are you doing that? Wouldn't that be the same?
pure pressure. Why am I doing it? Pure pressure.
No. But why isn't it just alpha prime prime? Why is it alpha prime prime?
Oh, well, he will. I will forever after this write alpha prime prime. But you should understand that alpha prime is the velocity field along alpha. It's the velocity field of alpha along alpha, right? Is it?
Y'all in lab.
Oh.
They usually meet in here, but they're at an actual lab.
Oh. Oops. Well, I'm glad we didn't start doing this earlier, because I apparently would have been in the class. So,
We teach on that board, we teach on this board.
so alpha prime is the velocity field along alpha. That is a vector field on the surface, right?
Yeah.
But the second prime is the covariant derivative of alpha prime along alpha.
Why do we make this distinction?
Well, the first prime does not involve connection coefficients.
Yes.
The first prime just involves taking the curve, ripping it back to the parameter space derivative, differentiating the, the pre-image of the curve in the parameter space, and then pushing that thing back forward, back over here, as appropriate through the patch. But the covariant derivative involves these connection coefficients.
Where is it? Oh, we didn't use it at first, and now we're using it.
Yeah, it's a different thing. Like the second prime is a very different thing than the first prime. All right? Yeah, so alpha, whereas alpha prime prime is covariant derivative of alpha prime along alpha. Now, I think it is true in the context that we're on the plane, right, where the connection coefficients are 0. If you sort through all of this, the acceleration will literally drop back to the usual acceleration in calculus 3. But in the context of a curve space, this will be something new and interesting.
Yeah, because it's not just going to be a line.
Right, well, like the acceleration, I mean, this covariant derivative is, again, in the tangent space, right? The acceleration, if you take a curve, on a surface in 3 dimensions, you calculate its velocity. Yes, the velocity to the curve will be tangent to the surface,
Yeah.
but the acceleration need not be. The second derivative of the curve will give you an acceleration which has a tangential piece and a normal piece. The tangential piece, yes, will be tangent to the surface, but the normal piece need not be in the tangent plane. The normal direction to a curve on the surface, it doesn't have to do anything particularly nice. I mean, there's special curves where the Frenet normal lines up with the unit normal to the surface. We looked at those so-called principal sections or whatever. He uses a sigma in the book for those. But you see the acceleration to a curve in 3 dimensions, it need not be tangent. There can be another piece, a normal piece.
Yes.
But not for this. This is straight up tangent. This is a
Yeah,
tangent.
because in Calc 3, like, it could have been orthogonal, right?
Yeah. So the next lemma, here we go, lemma 3.4. It says if you have E1 and then E2, which is equal to J E1. J is that rotation by 90 degrees operator.
Yeah.
All right. So let this be a positively oriented frame.
Does that mean we're just restricting it from 0 to 90?
On M. Well, what that means is that the coframe theta 1 and theta 2, the wedge product of that matches the dm for the surface, which is to say that it's naturally dual to the normal to the surface. If we had one, But in the abstract, it just means that the dm, which is given for the surface, the 2 form, for surface to be oriented, we have to give a non-vanishing 2 form over the surface. If that non-vanishing 2 form is in the same, if it's equal to a function, a positive function times theta 1 wedge theta 2, then they have the same orientation. If it's minus theta 1 wedge theta 2 times some function, then it's the opposite orientation. You got 2 choices. Positively oriented frame field. And if y is a vector field of constant length, I'll say all right, along alpha in M, then if phi is the angle function from E1 to Y, all right, then Y prime is equal to phi prime plus omega 1, 2 alpha prime times j of y. Let me foolishly attempt a picture of some of the things that are being said here. So, you know, you've got this curve, alpha, right? Along alpha, you have I mean, I'm not sure exactly where E1 is. I'm not saying that E1 is necessarily tangent to the curve, right? That's not being said. But you also have y. All right. And so to get from E1 to y, there's some angle that you sweep. All right? We're calling that, yeah, well, that's what we're calling phi. The angle function. I mean, that the fact that there exists such an angle should be clear from the fact that we're working in 2 dimensions, right? And we have the frame E1 to work with. And, okay, so the formula for y in terms of the angle function and E1 and E2 is as follows. It's cosine of phi E1 because that's the part of y which is in the E1 direction, right? And then plus sine of phi E2. And that I know that because it's a positively oriented, just what's given about how E1 and E2 are situated. Well, anyway, or you could take this to define, anyway, this defines phi, essentially, this formula. And, but E2 is given to be j of E1, right? So, okay, so let's work through the mechanics here. This is a covariant derivative, right? So this here is F1, this here is F2, right? And what was our definition? Y prime is F1 prime I mean, here's the definition right here, right? So we go through it. So what's the derivative? What's f1 prime? Well, it's minus sine phi phi prime, right? That's my f1 prime. And then plus f2, right? Plus f2, well, plus this piece right here, right? f2, which was sine phi, and then omega 2, 1 of what? Of alpha prime? What's alpha prime here? Well, it's alpha prime, right? All that times E1. And then plus what? Plus f2 prime, which is cosine phi, phi prime, plus f1, which was cosine phi, omega 1, 2, alpha prime, all of that times E2, right? All I did in red was just apply the definition of covariant derivative to our current context. And then what you want to do is group together. Well, you see we got a common story here, right? We've got, if you tilt your head and squint, you can see what we're really looking at here is phi prime plus omega 1, 2 alpha prime, all right? And so we've got minus sine phi E1, right? So see that? This is this, and that gives me this piece, right? And the omega 1, 2 alpha prime, let's see here. This one right here, omega 1, 2 alpha prime, when I flip that over, I get the minus, which gives me that term. So these first two terms give me this, right? Give me that. And then plus what? Plus over here, plus cosine phi E2. That's from this term over here. See, because I've got a phi prime and a omega 1, 2 of alpha prime there as well.
So you flipped omega 2, 1 to equal negative 1, 2?
Yeah, exactly.
Okay.
Yep.
Okay.
Yeah, we can do that.
And that's where you get that. Wait, but wouldn't that make sine phi positive?
No, there's a minus there, but that's okay. Let's see here, because I say that that's j of y. Let's see here.
Wait, then, no, that keeps its minus. I mean the cosine. Sorry.
Well, the cosines,
No. You pulled out a 1, 2, but
yes, that's from this right here. There's a minus on that one already, right?
yeah.
And this becomes minus when you change it to omega 1, 2. Over here, on the other hand, it's already 1, 2, and it's plus cosine, so it's just that.
So why do you keep the minus then?
Because it's there. I mean, it's
No, I
there.
get that, but I'm saying if you flip.
Well, then that would flip the cosine to minus.
No, it's not.
Oh.
Okay. Okay, so we flipped omega 2, 1 and 1, 2, giving us a negative. Right?
Mm-hmm.
Where did that negative go? Is where I'm at, is what I'm asking.
This one?
Yeah, the one you pulled out, that should be a negative.
Well, there's a minus on both of them. So I pulled that minus out and put it over here.
Yes.
Now, the larger point here, and maybe I can draw a picture of this, is, okay, so like, oh, well, sorry, velocity. So now you've got, here's your, oh man, here's your curve. Here's E1, right? Here's E2, let's say, which is, by the way, J of E1. Okay? And this is, let's say this is Y, right? J, so JY, it's over here. Because it's this J operator rotates.
Oh.
So check it out. This angle was phi.
And that also would be phi, right?
This would also be phi.
And that would also be phi with geometry.
So what, let's see here. Yeah, I suppose you could put phi back here, right?
Yeah.
And so then you can see that J of Y is what? It's equal to minus cosine phi E1, right?
Yeah.
Plus sine phi E2, right? Which is this.
Wait, backwards.
Right. The only thing that's wrong with my current discussion is I've assumed that C is equal to 1. Like, I can't write this right here, this star equation, totally bogus, unless I know that the length of y is 1, right? You can't choose a cosine and a sine like this to express the vector field unless you know the length of the vector field is cosine squared plus sine squared, which is 1.
I'm sorry, I'm still stuck on the JY2. When you
Did I?
No, are you saying that JY?
I must have done it wrong.
No, it's just because it looks like phi is 45 degrees, but you're saying it's phi is some arbitrary angle, but those two are equal to each other, degree angle, because that's what we define.
Oh,
right?
yeah. Well, you're right. This angle should not be phi up here. That's not right. And I'm not.
Did you define J as a 90-degree rotation?
Yeah, J is a 90-degree rotation.
Yeah, phi. That's also going to be phi, and that angle is going to be 90, but that should be.
So this would, yeah, this wouldn't be phi. This would be 90 minus phi, right?
No, because those are both 90-degree angles.
I think that has to be complementary to that because the sum of this and this is 180.
Well, you can take a 90 out. And 90 plus phi.
My point is that this one in the middle is 90 degrees,
Yes.
and this is not right either, right? So if I made this minus cosine of 90 minus phi E1 plus the sine of 90 minus phi E2, then how does that work out? What's cosine of 90 minus phi equal to? It's cosine,
Oh, yeah.
cosine minus sine sine, yeah.
It wouldn't be 1 or 0.
I believe that is minus sine of phi. And this one, sine, cosine,
Oh, I see what you're doing.
that one's plus cosine phi E2 when you work through the trigonometry there,
Yeah.
which I should have done because then
And then that matches. Yeah.
then they match up. Thank you, though. I was being too cavalier about my my geometry there. All of this said,